Okay, so if you recall last time we were talking about propositions, well, proposition is just a sentence, it's either true or it's false. And then we have these propositional forms, which are made up of propositions that are hooked together by connectives and or negation, things like this. The last thing we had is this definition. If you have two propositional forms, we say they're equivalent if they have the same truth tables. They're made of the same propositions, different connectives. And a simple example of this. P and not P will have the same truth table. Give you another definition here. And there the pattern is broken. Let P1 up to Pn be propositions and S a proposition form from this. P proposition form. So S is a propositional form of sentence we make out of these smaller propositions. We say S is a has anybody ever heard this word before, tautology? Anybody know what it means? We say that S is a tautology if S is true for any choices of truth values for P1, P2. And on the other hand, we say it is a contradiction if it's false. If S is false. For all choices of truth values. For one. Yeah. And finally, we say that a denial of P1, so I'm just going to pick one of the propositions P1. A denial of P1 is a proposition equivalent to not. So a denial of a proposition is just a proposition that's equivalent to the negation of P1. Okay, so let's kind of talk about this a little bit. I mean, can anybody give me an example of a tautology? That is some propositional form I can make, and no matter how I choose the truth values of little propositions in it, it's always true.
It's cold or it's not.
Okay, essentially I can generalize your example. So how about this? Any sentence you want, any proposition or not P. It's cold or it's not, right? Because, okay, so this is kind of silly, but let me do the truth table here. Well, there's only two ways to assign. There's only one proposition here, so that's easy. P is either true or false. And if P is true, then not P is false. And if P is false, then not P is true. And this is an or. So all you need is one T. So in both cases, so this is tautology. All right. Can anybody give an example of contradiction?
He and not.
Okay. Or I'm going to be even more of a lazy person. Right. This one was a tautology. Not of that has to reverse both of these values in the truth table. So it's got to be false, false, right? Everybody agree? And what was it that you said?
I was saying he and not.
And this, he said something different, right? But what he said is equivalent to mine. He said he and not. Two different statements, but the same truth tables. These are both contradictions, and the two statements, although different, are. Everybody agree? Let me give you a quick example here of a denial. Okay, one example of a denial. So if I walk up to you on the street and I give you the proposition P1 and I said, give me a denial, here's an easy thing you can do. How about not P1, right? But oftentimes there are other denials. Let me give you an example of a denial of P1 that's not just not P1. Not P1. This is equivalent to not P1, right? And so it's a denial, but it's strictly speaking, it's not just not P1. Any questions on that? How about this? Let me see if we can see. Give a denial of P or Q.
If he is it's Sunday, the denial of Q would be it's Tuesday.
Oh, well, I want one like more that deals with this more general thing. Okay, I'm gonna give you a smart aleck answer first. Yes.
I was going to say, I guess it would be not. Actually, I don't know what I was going to say not P and Q, but that's not right.
Close. Let's check this. Okay, let's look at the truth table for just P or Q first. So, so I guess I'm gonna need 4 here. True, true, false, false, true, false, true, false. Okay, so let's see what P or Q is. Now remember, for the or, I only need one of them to be true, correct? So the only way that this is false is if it's a double false. Right. Now, of course, let me just add a column to this. Because certainly, my first example has got to be true, right? It's the negation of this. So one denial is always negation. So this is false, 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 true. Well, let's test this other one that we have here. Not P and not Q. So let's see if the table, false, false. Uh, false. Okay, there are possible P and Q. So not P should reverse this first column. Measure. Not Q should reverse the second column. False, true, false, true. And let's see what we get here. Not P and not Q. Okay, so we've got to look at these columns. This is an and, right? So the only way to get a T here is you got to pair up on the T's. Everybody agree with that? The only way that we pair up on the T's is right here. And notice the truth table for this is equal to the truth table for this. These are different statements, but they're equivalent. So this statement is equivalent to this, so this is a denial of P or Q. Everybody okay? Questions? Okay. Right. Now I'm going to talk about lack conditions, implications. Conditions and by conditions. Okay, so let me give you this implication arrow definition. I'm sure that you all have heard, just in regular speak, things like implication and this implies this and so forth. Let's be careful about what we want this to mean mathematically. Definition. Suppose the P and Q are propositions. The conditional sentence and there's sort of two terminologies that I will use for this. If P, then Q, or P implies Q. Is a proposition. By the way, anybody want, what's the correct definition here? So P implies Q. When should this be true, do you think?
When he's true.
When
Uh,
for every Q that's true, P is also Q.
okay, so what are our working hypotheses? If P is true, well, what if my statement was something like this? Let me think of something that's true. 2 + 3 = 5 implies that all politicians are Republicans. Does that seem like a true statement? Well, let's take politics out of it, right? This is true precisely when P is false or Q is true. So the implication P implies Q, and this is the Q is true. Something implies something true. You want this outcome to be true, right? This one's a little bit easier to understand, but this implication is always true. P is false. If Jim's name starts with a J, then water is wet. I think we would all kind of, you're comfortable with that perhaps, because water is wet, right? If Jim's name begins with a K, then water is dry. Now that makes people feel a little uncomfortable because water is not dry, right? But this is conditional. If Jim's name begins with a K, and it doesn't, right? So you can just trash it out immediately. And that's why P is false makes this implication true. If this is false, doesn't matter if this is true or not, the implication is true. So the truth table looks like this. If the condition that the statement is based on, P implies Q, if this is false, then you don't even get to consider this arrow. This is already true. And the only way this fails is if P is true and Q is false, right? You can't have something true implying something that's false. That is the only failure for this to be true. Does everybody kind of see why we might want this done?
I have
So,
a question.
I'm sorry, what was that?
I just have a question.
Sure.
Could you give another example of like P being false but Q being true, and then the implication being true?
Oh, everything, right? If you start with a false statement, if P is false, then P implies Q, no matter if Q is true or false. Okay. So think of it this way. uh. If, uh. If Jim owns, a Corolla, then Jim owns a car. Would everybody agree that that's a true statement? Corolla implies car. Corolla implies car. Everybody okay with that? If I make the statement, if Jim is a dog, then Jim owns a Lexus. That's a true statement because at the outset, I'm not a dog, despite what some people in my past might say. And so you don't get to carry on after that, right? Jim is a dog implies Jim drives a Lexus. I'm not a dog, so no longer applies. And that's sort of why that works. Does that kind of clear it up for you?
Yes, thank you.
Well, one of my favorite sort of implication things. So let me do another example about this. And I'm going to show you an application this in a moment. How many of you have seen The Wizard of Oz? And I don't mean the new movie out, but like the classic one with the flying monkeys from 1939. Everybody's seen that, right? Do y'all remember when Dorothy gets landed in Oz? They drop the house on the witch and she comes out and she meets Glinda. Does anybody remember what? It's always bothered me when I was a kid. So the conversation in the movie, Dorothy comes out and Glinda says, "Are you a good witch or a bad witch?" And Dorothy says, "Oh, witches are old and ugly." And Glinda says, "Only bad witches are ugly." Question: did Glinda just insult Dorothy?
And
Now, of course,
ugly witch implies bad witch, but bad witch does not necessarily imply ugly witch.
right. So let's be careful about this. And the first thing is, let me give the following disclaimer. Both bad and ugly are a subjective term. So let's just pretend that everybody agrees on what ugly is and everybody agrees on what bad is, right? What does this statement say? Only bad witches are ugly. Does that mean that if you're bad, you're ugly?
No.
What does it mean?
It means that if you're ugly, you're bad.
Bad spelling. B is bad witch, right? That's something that's either true or false. Q is ugly. That's something that we will assume to be either true or false. Can we write Glinda's statement in terms of a conditional?
You implies
Okay, so this is our working thing.
verse not.
If you're ugly, then you're bad. Is that what Glinda said? If you're ugly, then you're bad.
Wouldn't be implied.
Well, so think of it this way. Let's take Glinda's statement. Suppose you see an ugly witch. Can the ugly witch be good? And if we're assuming that there's only bad witches and good witches, then this does mean that ugly implies bad, right? Uh. Okay, well, I know what the truth table is supposed to be, so let's just think about this in terms of one statement, all right? If you see a witch that's ugly, does it mean that the witch is bad? Linda said that only bad witches are ugly, so if you see one that's ugly, it's gotta be bad. Everybody agree with that? And so by that logic, this one has to be false. Now, let's suppose that you see a witch that is pretty. What do you know about that? Does that mean that the witch is good?
No,
No. So if you see an ugly witch, does that, if you see an ugly witch, can she be bad?
possibly.
Right, so the outcome here, so ugly implies bad has to have this truth table. Does this hold up to what one of the saying? She says only bad witches are ugly. Is this the same? This is the truth table.
The converse statement would be, the witch not being bad implies not being ugly.
Okay, run that by me again.
Wouldn't the converse be a witch that is not bad implies the witch is not ugly?
Okay, so what the converse, so we're getting ahead of ourselves here because I want to introduce this. The converse of this statement is if a witch is bad, the witch must be ugly. Right,
So
so
that'd be interesting.
so I think what you're trying to do is go for the composite. So anyway, so think about this truth table. So I'll leave this as an exercise for right now. Is this the same as Glenda's statement? Another way to think of Glenda's statement, so think about this with your exercise. Let me do kind of a diagram here. Which is good, which is
Wouldn't only bad witches are ugly imply that no other witch is ugly? Like if you are a bad.
Okay,
witch,
so
you have to. And
it
it's
says-
not ugly, you're a good witch. This is only two possible choices.
it says only bad witches
Only bad witches.
are ugly.
Yeah.
So if I were to draw a circle that means the ugly witches,
Yeah.
how would I draw them?
I don't think you would draw it in the good circle, draw the ugly circle, side, bad circle.
That is correct. Everybody agree with that? This is really what Glenda's saying, right? That if you're ugly, you have to be bad, right? There's no ugly witch that's good. That's what she said. So all the ugly witches are a subset of the bad witches. Everybody agree with that? Everything that's left over, ostensibly, is a not ugly witch, right? And this leaves open the possibility. What does it tell me? It tells me, what does it say that if you're a good witch, what's true?
Pretty.
You're pretty. What does it say if you're a bad witch? Maybe, maybe not. Everybody agree with that? Right? If you're over here in the bad witches, you might be here, but it's possible that you're out here. Right? It's certainly true that maybe every bad witch is ugly, but that's left open by one statement. Everybody agree with that? Okay, any questions on that? Let me once again examine this truth table for P implies Q over here. And this is actually one of a number of proof methods that we're going to talk about. Let me give you a very silly example to sort of simply show a proof technique here. So examine proof technique for now notice that this is only false one time. Everybody agree? The only way that this is false is if P is true and Q is false. Everybody agree? So this actually gives us some leverage in the following sense. Right. When are, look at the truth table, when are both P and P implies Q true? Here, and that's it. Everybody agree? Because every other time, either P implies Q is false or P is false. Agree? So if you know if you know if you know that P and P implies Q are true, then Q is true. And this is a proof technique called modus ponens, which is Latin for, I don't speak Latin. But let me give you an example of how you might use this. Let me give you a conditional statement. Uh, follow conditional statement. So how can I redo this sort of as a conditional statement? So I wrote that kind of in English. Jim teaches on Mondays.
If Jim is teaching something,
Uh,
the Jim teaching, why is it?
yeah, it's the other way around, right? Because what it really says is Jim teaches on Monday. So, you know, if it's Monday, then Jim teaches. Right? Everybody okay with that? Everybody okay with that? Monday, it's Monday implies Jim teaches. Right. So, So if it's Monday, so if we know, you look at the schedule and you see every Monday I teach. So now you know if it's Monday, Jim's teaching. Now, suppose that you know it's Monday. This is P, and you also know P implies Q. P implies Q is true because Jim teaches on Monday. You also know that it's Monday. What can you conclude? That Jim teaches. And this is the modus ponens is often a way that you can prove things. You know that P implies Q, you know that P is true, and so therefore you can conclude that Q is true. Okay, any questions? So I'm gonna get to what you were bringing up a moment ago, with all this business about converse and so forth. Definition. Let P and Q be propositions. We define number one, the converse of P implies Q is just turn the arrow in the other direction. Q implies P. These are definitions. I'm not making any claims about them being true or whatever. But if I have A implies B, the converse is B implies A. Just turn the arrow around. How many of you, by the way, ever heard of that? Converse actually is something that's brought up oftentimes in sort of regular communication. That's what it is. Carefully, the contrapositive of P implies Q is, anybody know what this one is?
That would be the, if not Q, is not P.
The contrapositive, P implies Q, is arrow going backwards with the knots, right? Not Q, other direction and not P. And finally, this is the one that you need to know what this is, but it's the first two are more important, I think. The opposite of implies Q is not P implies not Q. Okay. All right. I've got a little game for you. One of these, exactly one, is equivalent to P implies Q. Anybody know which one it is?
The contrapositive.
It's the contrapositive.
And the other two are equivalent to each other.
Ah, very nice. So, here. In fact, I'll throw that in. How about that? consider this conditional, sentence. P implies Q is equivalent to, it's kind of a problem. But not to its converse or opposite in general. Well, let me show you why the converse is never going to work. Let me give you a, yes, sir.
When I was young, I had an example of this, that I thought if it was below freezing, then it would snow.
Oh,
Instead, it
Right.
was snowing.
right. So here's a, so if I have a Lexus, then I have a car. Everybody agree with that? That's conditional statement is true. If I have a Lexus, then if I own a Lexus, then I own a car, right? Is the converse of that statement true? If I own a car, then I own a Lexus? That is certainly not true in general. And if you don't believe that, walk out to the parking lot and see that McDonald's dumpster with an engine that I drive, and you will see that the converse is not true in general. However, let's be more careful and do a truth table. The opposite of P plus Q is equivalent to the converse. Um, let's do the truth tables. Actually, let me put up the spread this out a bit here. Okay, so let's do some truth tables. So we know that this is false. There's being positive, right? The converse is not Q implies not P. Well, let's see what happens here. Not Q is as follows. Not Q is false, true, false, true. And not P is false, false, true, true. Everybody okay? And so not P, I'm sorry, not Q implies not P. Let's see, this is true if either this is true or this is false. So let's see, this is false here, here, and it's true, true here. Okay, this is true, and this is false, so it's false. Notice we have a match. Right. And the converse I'll do one more. I won't do the opposite. I'll let you all kind of figure that out, but the converse. Well, let's go back here. This should be true if Q is false. Oh, I'm sorry, if Q is false, this should be true. So it should be true here and here. It's true here. Oh, my bad. And let's see what we've got. Q must be true, false. Notice that Q implies P has a different truth table than P implies. Everybody okay? By the way, can somebody tell me, I'll leave this for an exercise, see if you can figure this out. The opposite, I made this last claim that the oh, let's see, this is equivalent to converse, and this is equivalent to it. Oh, right. Converse. Right, so can somebody explain why the opposite and the converse are?
Because the opposite of the original is the contrapositive of the converse.
That's right. If you look at the contrapositive of the converse, you get the opposite. And so check that out. Look at the table of the converse, which we have over there, and check that against the opposite, and you will get the same table. Okay. Any questions so far? Okay. Now, one of the most important things that can happen in math, oftentimes what you're doing is you're trying to show things are the same in a looser sense, right? You all seen this in geometry, like, what do you do? And of course, if you're physics, and I know I've got a bunch of physics people in here, you do a lot of kind of geometric things. What do you know about similar triangles, right? Similar triangles have the same, they have the same angles, right? And they have proportional sides. This is very important in doing like calculations about physics and engineering and so forth, right? Are two similar triangles equal? Well, not necessarily, right? I can have an equilateral triangle of side length a mile or an equilateral triangle of side length 1 inch, right? But they're sort of the same, right? It's only a matter of scale, right? In mathematics, this is often what we talk about when we talk about equivalence or things being equivalent, is maybe they're not equal, but close enough for rock and roll, and we can like use it to do important things. So yeah, propositions. Then the conditional. Sentence here. Notice I've got arrows on both heads. P, if, and only if Q. Sometimes I'll have P, if, and only if Q. If you ever see me put two F's on the if, that doesn't mean I'm having a stroke. It means that this means if and only if. It's a standard short type. What do you mean? What do you suppose this means?
These will be true.
That is right. That is correct. This is true exactly when P and Q have same truth tables. Another way to think of this is both P implies Q and the converse, Q implies P, are both true. Okay. Any questions on it? Everybody understand what we were talking about so far? You guys get it so far? I invite you to look at theorem 1, 2, 6 for next time. I'm going to give you a long line of like propositions that are equivalent, have the same truth tables. It might help to look over that, get kind of warmed up. Other than that, you all stay safe, and I will see you on Monday. Oh, any questions out there in Zoom land?